Okay, in previous lectures, we had been talking about how a prism was used to create a monochromator. And the prism works by taking the different wavelengths of light and spreading them out into a spectrum where they can be selected by some slit. The problem with using a prism, however, is because of reflective loss. Anytime you travel between different media that has different refractive indices, you end up scattering or reflecting a lot of light off that surface. In fact, between air and glass, you end up losing about 7% of the light. So a lot of the light gets reflected before it allows it to transfer through to the monochromator slit. To avoid this problem, there's another way to create a a diffraction pattern, and that is by running light through a slit. Anytime you run light through a small slit, there is a diffraction pattern that is created. And this angle of diffraction as the light goes through the slit is actually wavelength dependent. So blue light will have a different angle than the red light. Ultimately, what happens is that when light goes through a slit, it creates a rainbow pattern. And that rainbow pattern is the diffraction of light. The nice thing about the slit is that the slit doesn't have any reflective loss because you don't change between the media. The smaller you make this slit width of the diffraction grating, so this width, the bigger the diffraction becomes. This is the principle of what we're going to be talking about, which is a diffraction grating. Now, diffraction grating really is just going to look like a mirror where the light comes in and the light comes off. But if you look at it really, really close, there is a sawtooth pattern cut into the surface of the mirror. And what happens is each of these little distances right there, each of those tiny little differences between the sawtooth acts like a slit to the light that's bouncing off of it. So if the light comes in at an angle, then that would be normal to the plane of the mirror. It's going to be reflected off at some angle which is dependent on its wavelength. Okay, so here, red light comes in, blue light comes in, green light comes in, and they are all coming in at different angles. As you can tell then, this angular dependence of this reflection off this surface can create the diffraction pattern that would allow us to use a slit to create a delta lambda, or the monochromator. So instead of the prism creating the diffraction pattern, we're going to use a diffraction grating to create the diffraction pattern. What that would look like would be that the white light would come in towards this mirror and bounce off, and the reds would come one way, the greens, so the light bounces off the diffraction grating and creates the diffraction pattern. The angle, we can calculate these angles such that the sine of the reflected angle R is equal to n lambda over d minus sine of the incident angle, where this is the size of the slit width d. This is the wavelength of light or radiation coming in, and n is the harmonic. Now the harmonic means that when you have a diffraction pattern, it will set up ripples of diffraction patterns. All right, the simplest explanation is if you look at a rainbow, you see one really bright rainbow. And if there's a really bright source, sometimes you can see a faint second rainbow or a double rainbow. And sometimes even possibly you can see a third one. The second and third ones are the harmonics, and they are always of lower intensity. So we always work with the first harmonic, where n is equal to 1. So whenever you're using a diffraction grating, you operate on the first harmonic, the brightest rainbow, and n equals 1. From this equation, though, you can see that the angle of reflection is dependent upon the wavelength, inversely proportional to the size of the slit that it's going through. So the tinier the slit, the bigger the dispersion. So, now this is the diffraction slit. The smaller the diffraction slit D means greater dispersion. Little teeny tiny slit, you get a really wide rainbow. Big slit, you get a very small amount of dispersion. That means small slit equals small linear reciprocal dispersion. Remember, linear reciprocal dispersion is reciprocal, so small d to the minus 1 means really big dispersion. The d to the minus 1 of a diffraction grating, which is still delta lambda over delta x, is equal to d the diffraction slit width divided by NF. That's the harmonic, which is 1, and that is the focal length. Should make sense to you that the focal length is going to play a role if it's angularly dependent. Look, let's look at it this way. If we have this kind of angular dependence of the reflection, then if I put the focal distance or the focal plane here, this distance f would have a very small distance of diffraction. But if I move the focal plane back out here, delta x gets bigger. So bigger delta x with the longer focal distance. Bigger dispersion means more dispersion here, which means a smaller d to the minus 1, because d to the minus 1 is inversely proportional to the amount of dispersion. We'll pick this up in a later video.